sunny day. And I've been working on a scour monitoring system utilizing magnetostrictive materials. And so I'm going to present the work I've done on that today. So first, we need to actually talk about what scour is. The formal definition is the removal of sediments such as sand or rocks from around bridge abutments or piers. And essentially what this means is it's basically the erosion of the riverbed underneath piers or important structures that we don't want it to be eroding around. And so why do we care about scour? Well, it's the most common cause of bridge failure. It's very difficult to detect because the water may be murky, it could be rough, so hard to see. There are thousands of bridges over 1,000 bridges in the state of Maryland alone. So there's just numerous. It's a large task to monitor this many bridges. And furthermore, it's always in flux. During a Hurricane Sandy, you could get a 10-foot scour hole and have it just be filled right back over by the time you're able to come check on it, and you'll never have known that the bridge was in any danger of collapsing. So what are some of the high-tech solutions already out there to solve this problem? Well, you have some things like sonar detection, which it works except for if there's debris in the water or possibly if it gets too rough, it can sometimes not have that great of an image or be that reliable. And furthermore, sonar detection systems are very expensive, so it's not really all that easy to implement it on thousands of bridges. You have other solutions which are a little cheaper and simpler, such as sliding collars, a collar that will essentially fall with the riverbed while it erodes. So based on the height of the collar, you can tell how bad the scour is. And then you also have these things called floating beacons, where they're buried prior to any scour event, and as it scours under, the beacon will float to the top and send out a signal. These are good ideas, and they are viable, except for the fact that, as we talked about earlier, scour is in constant flux. So these are one-time uses where you want a monitoring system that can, after one scour event occurs, you don't have to replace the whole system. So while these are the high-tech solutions that people are either investigating or implementing, the most common solutions are one, using scuba divers to go down into deep bridges and actually visually inspect the bridge piers, which, as you can imagine, you have to shut down the bridge, you have to find a diver, so it's very expensive, very inefficient. And actually, by and large, the most popular method for checking bridge scour is a long stick or a sounding rod. So what this is, so members of the Department of Transportation will go out there with sounding rods and literally just go alongside the bridge and determine the depths and record it. And while this is what they do now, so it's viable, it's not very efficient, and you're also not going to send poor Pete out there in the middle of Hurricane Sandy to check how bad the scour is. So you're not getting any live data during the real inclement weather. So what's our proposed solution? Our solution involves attaching flow sensors to the pier at known depths. And so you have flow sensors that are in the water and will move around when the water flows past it. And then you have sensors that are buried. And those sensors will be in one place and give you a static signal. So knowing the depth of each signal and whether it's giving either a dynamic or a static signal, you can tell how deep the riverbed is and how bad the scour is. And one reason, why hasn't this been, it's a very simple idea, so why hasn't it been implemented before? Well, the need for a robust sensor is really the biggest reason. Until structural magnetostrictive materials like we're going to talk about, this wasn't very viable because the sensors weren't robust enough to take the debris or the corrosion in the rivers. So, as I said, we're going to use magnetostrictive whiskers, so let's kind of go over some of the magnetostriction basics. So you can use magnetostrictive materials as either actuators or sensors. And to use magnetostrictive materials as an actuator, you use what's called the Joule effect. Okay, it's running. Essentially, you take a pre-stressed magnetostrictive material and you introduce a magnetic domain to it, and this will cause the dipoles or the magnetic dipoles to rotate within the material and cause an exertion of a force that you can use to either move a mass or just simply apply a force. To use a magnetostrictive material as a sensor, which is what we do, we use the Villari effect. This is the converse. The converse to the Joule effect. So now, instead of introducing a magnetic field, we place a magnetic field there already, which aligns our dipoles nice and straight. And now, when you when you actually compress or just stress the magnetostrictive material in any way, it'll force the dipoles into an unaligned state, causing a change in magnetic induction that you can pick up. And I guess in this situation, it should actually probably be one less instead of more. I missed that one. So let's look at the equation for the Villari effect. So as I said, we'll measure magnetic induction, and you have two terms that affect the magnetic induction in the Villari effect. You have the permeability of the material and the applied magnetic field to that permeability, and then you have the effects of magnetostriction. And so as we said, you have to introduce an external magnetic field in order for it to work as a sensor. So, and why is this? Just some figures to help understand. So if you took just a magnetostrictive material that's even textured, the dipoles are still going to be somewhat random. They're going to be aligned in the minimal energy, in a state where they have to exert the least amount of energy. And so if we take these somewhat randomly dispersed dipoles and compress them or stress them in some way, they'll bunch up together. You'll probably actually get some random change in magnetic flux, but it's not going to be really much or enough to measure. So you introduce the magnetic field, everything's aligned. Now you compress them. The magnetic domains are aligned very differently than they were before, causing a large change in magnetic flux. So now that we have the basics of magnetostriction down, let's look at the materials that you can use, some magnetostrictive materials. So the most classic magnetostrictive material is terphenol D, and this is what you typically use or thought of when you work with magnetostrictive materials. The problem for us is it's extremely brittle, so it's not great for the robust sensors that we want to create, and actually has a problem. You have a problem creating them into sensors, turning them into sensors. You could actually use just straight iron and nickel. They exert some magnetostrictive properties themselves, but the magnetostrictive properties are not the magnetostriction is not nearly high enough for what we need to use it for. But they would be nice and ductile. So thankfully, friends at Carter Naval Labs came up with iron gallium, or galphenol as we call it. Now its magnetostriction is not nearly as high as terphenol D, but it's a lot higher than iron and nickel, and it allows us to use it for what we need it for, which is to create our sensors. And it's much more ductile, and it's actually the first structural magnetostrictive material that ever created. And what that allows us to do is it actually allows us to roll it, or Dr. Knopf to roll it, and turn it into a flat sheet, which can then be cut into the whiskers that we use. Without it being a structural material, we couldn't create these whiskers, as the terphenol would just crumble. And here in our labs, Dr. Na has actually been working with iron aluminum, or alphenol, which has slightly less magnetostriction than galphenol, but it's not a noticeable drop-off, but it has it has an increase in ductility, which is actually very noticeable. We want our whiskers to be as flexible as possible. So, now let's talk a little bit about how the whisker design itself. It's bio-inspired from sea mammals, primarily harbor seals, which you can use their whiskers to sense the change in flow from, say, a fish that it wants to eat from several yards away, or I think several hundred yards away actually. And so when you actually break down a whisker, it's effectively a cantilever beam, which is what our sensors are designed. So we essentially have our galphenol whisker, which acts like the seal's whisker, and you have the root where all the stresses are applied, and the domains rotated, and some kind of magnetic sensor, which for us is a Hall sensor, that can pick up this change in magnetic induction. So we can actually look at the actual components we do. As I mentioned, this is the basic design. The black line represents the alphenol or galphenol whisker. We have a Hall effect sensor right at the root to take care of, to pick up changes in magnetic induction due to magnetostriction. And then the biasing magnet somewhere at the back of the sensor so that we can, to align the domains, so that we can get, maximize the change in magnetic flux. So here's a picture of what a whisker looks like. You see the Hall sensor here, the small biasing magnet, Ideally, the Hall sensor would actually be right under the stress point of stress concentration, or the root of the cantilever beam. But and we actually have a lot of sensors like this. But for visual purposes, so you guys can actually see the Hall sensor, I figured this would be a better figure. And this also still works, even being behind the the point of stress concentration. And to get a look of how the dipoles look, the magnetic dipoles look inside of it, you have nice aligned dipoles before it's been in the undeflected state. And then when you compress it, or when you deflect it, like any beam, you get one side of the beam in full tension and the other side of the beam in compression. And the side in tension doesn't really change a whole lot. It's in tension and it gets more space, so it's not going to rotate itself. But the side in compression has its volume constricted, and that's what causes its magnetic dipoles to rotate, and that's what we're going to be seeing in our Hall sensor. So we actually have a video of one of these sensors in action using actually the same setup you see here. So, thought we had muted. So you, as you see, it's very responsive to its touch, and the whisker is very flexible, and we can actually do the same thing here. And any reaction is immediate, or any sense is immediate. So it's very sensitive to deflections, as we hoped it would be for the river flow. And these are actually newer whiskers than those, so these are actually even more flexible and more easily oscillated.
Is the really high frequency stuff noise on there, or is that actually?
Not so. It depends. So right now that's noise. But if I do that's actually the signal. Let's see, what would
So
that
it
be?
rescales itself or something?
So if I actually kind of play around, you can do it slower. You can actually see the
Yeah.
effects. So let's look at the overall post concept. As I said, we'd like to, not only would you put this on the side of a pier, that's only really for new bridges. You'd actually, for current bridges, you can install this on a post. So you align your whiskers at known depths. You have them all report to some kind of DAC system, which that needs to be low powered because we'd like these things to last for a while, because it kind of loses its efficiency if you have to go replace it every 2 years or so. And you have to have a battery that can withstand the life cycle of the product. And ideally, we'd actually have this wirelessly communicate to the shore. That gets a little tricky as water likes to absorb radio signals pretty easily. So this is the wireless communication from the post to the shore, something we're going to be working on in the future. Let's also look at how the whiskers perform in flow. So this is in the water tunnel that's in Kim Building, and you can see it deflects very nicely upon startup, and it stays there. The problem is it deflects so nicely that, when you compare the whisker not underflow and the whisker inflow, we discovered they're almost indistinguishable. And since these sensors are made so that it can take plastic deformations and still work, you can't really give some baseline voltage. So the only difference between the undeflected and the deflected is the voltage, but we don't know what voltage is we don't have any baseline voltage to actually compare it to. So we have to figure out a way to make the sensors give an actual dynamic signal. They can't just statically deflect. Because if we bury them, they could be buried in a deflected state as well. So to do this, we tried a whole bunch of shapes. We tried fat whiskers, skinny whiskers. We tried really long whiskers. We tried crazy squirrely whiskers. We tried tree whiskers. We tried some more tree whiskers. We tried a little bit of bribery. And then finally, we did actually find that none of these really worked. They all did the same thing. It seems like the dampening properties of water are just good enough that, are strong enough that it was just overpowering any of our attempts to oscillate it. Except one thing did work, which was the attachment of an unstable airfoil, a dynamically unstable, which put the CG so far back in the airfoil that it caused it to oscillate. And this, like I said, this actually did work, but we are trying to avoid attaching things to the whisker that might catch on the seaweed or anything like that. So while it did work, we kind of wanted to experiment with other ways. The good thing is, most rivers aren't steady stream like we just saw. It's better represented by, say, a transient period in the flume when you're starting it or changing the velocities. So that's what we started to look at as well. So we have you have your baseline no flow again, no water flowing with the whisker. And now in the transient response of the flume going back, the flume changing its velocity, you actually get a really nice, clear, distinguishably dynamic signal. So now that I had the whiskers all designed, we also needed a low power way to take the data and save it out at the whisker site, at the site. So we needed a portable DAC system. And for this, we started out and actually used throughout the whole time the Arduino platform. Specifically in the first revision, we used this Arduino, which is the Arduino Mega 2560. And so for me, this is actually somewhat of a spot of pride on the project because I came in barely knowing what Ohm's law was and got to where I feel pretty comfortable with electronics. So this was actually a great platform to start on as it simplifies some of the microcontroller programming language and some of the connections that you need to make. And so that's why we started with it, but it also has the added benefit that you can write a program for it and then bootload the open source Arduino platform onto other microcontrollers and use that same program on those microcontrollers. So if you want to switch microcontrollers, it's not a whole redoing of your process. So you need a brain. For a DAC system, you need a brain, and this is what we've been using. And also for a DAC system, you need something to tell you what time of day you're actually taking the data. Microcontrollers don't actually have date and time. They can just tell you how long it's been since they turned on. So this is a real-time clock and what's called a breakout board. It's just a circuit in a nice condensed board that will tell us that the microcontroller can query and figure out what time of day it is, so we know when we got our data sample. And finally, you need some place to actually save the data. And for this, we just used an SD card. Once again, a shield that has that does all the power conversion you need to talk to a SD card and has all the connections. And we talk to both of these devices via SPI, or Serial Peripheral Interface. It's just a way of communicating serially between electronic devices. So when you have these components, oh, and I actually did forget to mention, you also have to have analog digital converters, but they're already in this pre-made platform, or on the microcontroller themselves, actually. So, what's the process? Once you have all these components, what's the process to actually have it save data? First, the microcontroller needs to request a sample from the ADCs, and then it sits there and waits for the sample to be converted, the voltage being sent to it to be converted, and then once it receives the data back, or once it receives the input back from the ADCs, it immediately stores it into its RAM, and then it actually needs to get it into some kind of non-volatile memory that's not going to erase when we turn it off, so we write it to the SD card. And then with whatever time's left, it just sits and waits for the next point as defined by your sampling rate. So this process works great, but the problem is if you start adding a lot of sensors like we do, this cycle starts to take a long time. And so which means it needs to finish before you go on to the next point, which means you have to reduce your sampling rate quite a bit. And so the other problem is, say you try and find a sample rate that's too high and it doesn't finish, what it'll do is it'll just finish saying its point and say, oh, I'm late, and just start saving the next point. And now you've got unknown gaps between each of your points. So it's not the sample data rate you've defined, and you also have no idea what that data rate is. So to fix this, we implemented something called, we installed a operating system to the microcontroller. And the one we use is called NIL RTOS, so NIL Real-Time Operating System. It's a basic operating system that uses extremely low amount of RAM, so it doesn't take up space in your microcontroller. And what this allowed us to do is use threads, or prioritize threads, which for us, that helps us because you can take a task, say, that's not so important, like saving, or not so important that you get it done right on the exact moment. If you take a task that is extremely important, like, hey, I need to start taking the next data point, and the more important one can pause the less important one, override it, and say, I'm doing my thing first, and then return to the lower priority when it's done. And so that modifies our process quite a bit here. So now, instead, when it requests a data sample and it's waiting for the ADC to convert, it's also saving. And then it receives and immediately stores it to its RAM. And then as it saves, or as it's waiting for the next data point, it saves. And regardless of whether this is done or not, it starts the next data point. Now, the reason we don't lose that data point is the operating system utilizes what's called a FIFO buffer, or a first in, first out buffer. So when this takes over, it doesn't just erase the old point like it would in the old system. It keeps it in a buffer and remembers where it was in that buffer, and just keeps stacking points in the microchip's RAM until it actually has time to write them. So now it extends the amount. You can take the same microcontroller and get a much higher sampling rate from it. And for us, this really helped a lot. We were able to go from something like 100 samples per second to 500 samples per second. So with that, we created our first prototype. And it looks like most prototypes you'd expect. Just a bunch of pieces wired together. And this is actually what we used on our first install site. Here you have your Arduino pre-built platform, your real-time clock, your SD SD card, and then we have this 5-volt regulator is actually for the sensors, not for the Arduino. It has its own regulator on board. And then the problem with this pre-made board that Arduino sells is it's made so any hobbyist can pick it up and use it for a whole lot of projects. And so it has a bunch of components we don't need, but we also can't put them to sleep when we don't need them. So we only want to sample once per hour, and we can't. And so we'd rather just shut everything off and keep it low while we're not sampling, and this doesn't allow us to do that. So to simulate that, I actually added a relay to the device that connected the Arduino and sensors to the battery power, and another ATtiny85 microcontroller. Once again, bootloaded with Arduino. Like I said, that was the nice thing about it. You can throw it onto any chip you want and have the same programming platform. And so this really low power microcontroller was in charge of turning on the system for 60 seconds every hour, while turning off the system for every other time, for the rest of the amount of time, and which greatly reduces or increases the amount of battery life we can have. So, as I said, that was our initial prototype. We had a lot of improvements we could do to that. So, as I said, the Arduino board, the pre-made Arduino board consumes too much power. It doesn't allow for a true sleep cycle. It was huge. And another problem that I haven't talked about yet is the 10-bit ADC resolution. It's good for our, well, actually, let's look at it. So if you use a 10-bit ADC, you get about a resolution of 4.9 millivolts, which actually works for one of our slow sensors that we're going to talk about next, but it does not work for our whisper sensors. We need something much more, a much higher resolution, which is a 16-bit ADC. And for us, 0.08 millivolts, that's more than we need, but it's not over extraneous, but it's not much higher of a cost. So we decided to keep the fidelity. So using this, keeping this in mind, we decided to get rid of the pre-made board, make our own circuit that will be able to sleep because I won't have the non-sleeping components on there. Much smaller, and uses 16-bit ADCs, and that's what I call my hand-built DAC. So once again, a prototype, but a much cleaner prototype. You have these new ADCs that that can do 16 bits. I changed out the microcontroller for the microcontroller called the AT-Mega 1248-84P, and it's very similar to the last microcontroller we used, same speed, but it has much more RAM. So now I can get that sampling rate even higher because I can make my buffer bigger. Same RTC, new micro SD card does the same thing, just smaller package, and our power regulator. The only downside to this microcontroller is each ADC has 4 channels, but it only has one analog to digital converter. So it has a max rate of 840 samples per second, but if you divide that between all 4 sensors that it has to switch to, it can only do that divided by 4. So about 200 samples per second. That's not, and we wanted to do that faster. So what this does now is it just samples 4 channels, and then 1 minute of the first 4 channels, and 1 minute the next 4 channels, and you can do up to 16 channels. But it'll take 4 minutes instead of 1. And keep note, you can, this we'll talk about, well actually no, actually not. So one problem we actually experienced with this is, as you can see, while the front looks nice and clean, the back is still a prototype. And when I was jostling around or playing with it out in the field, a lot of times these wires, even though covered, would short each other out, or sometimes the flux would bridge the gap. This is before I realized I needed to use no clean flux. I now changed that. And also it had this one problem that didn't actually figure out till later, that it would just randomly restart. I couldn't figure it out. It would work for 2 minutes and then just turn off, turn on, turn off, turn on, and just keep restarting it. And it took me until the next DAC we'll talk about to figure it out, but it was actually the 5-volt regulator overheating. We were using 12-volt batteries, and it got very hot to the touch, but because they were rated for it, I figured it would be okay, that it wasn't, I didn't think about it being the regulator. Thankfully, one day a breeze came along, blew across my microcontroller, and it started working, and I realized that I threw a heatsink on it, and they worked great. So that was a big hurdle for the project, but fortuitously we kind of got out of it. So because it kept shorting and those took a long time to build, I returned to kind of the initial prototype, but with a development board that had, it's still Arduino based, but it's made by SparkFun. It takes off some of those high energy components that weren't necessary and that were preventing me from doing some sleeping. And so I used the original SD card board, the same RTC. So this is just essentially the first DAC replicated with a little bit of power improvement, because it was more reliable and I didn't have to worry about the wire shorting. Because also in the meantime I was designing our final revision, which is designed, and we finally got them in today, or not today, recently, and so now in the middle of constructing them. But I decided to design the board on the PCB DAC, get rid of all those extraneous wires that are causing me problems. And this is the picture of essentially every layer layered on top of each other. You have a top layer where I did all my routing to all the components. A ground layer, which I put underneath it to, 1, insulate it, and 2, to serve as my DAC's ground. Power layer, which serves power to all the components. To further mitigate the problem of the overheating, I actually now have separate voltage regulators for the sensors and the rest of the components. Oh, and for I mentioned, we also decreased the voltage of the battery we're using. That pretty much solved the problem right there. But for extra safety, I did that. And then a 3.3 volt power supply for the SD card reader, and then the bottom layer, which is just another routing layer. And so this is the future of our DACs, and this is kind of what I got excited about, learning how to CAD electronics, which I'd never done before, ordering PCBs and trying out. So I'm very excited to put this together and give it a try.
Who'd you order it from?
This one, I originally quoted it from Advanced Circuits, but they were pretty expensive, and I went through Sunstone.
Okay.
So, yeah. Have you heard of that?
No.
Huh? Oh, sorry, I thought that's the other question.
I just hadn't heard of them.
So yeah. It looks like it's going to work. I'll let you know how it turns out. Yeah. So, so then now let's actually start to look at some of the install sites. So we did install at 2 different sites. The first of which is over by Annapolis, Maryland, and it's a tidal site where basically the flow of the water changes direction with the tide. Actually, I'll get into that in a little bit. So it's kind of somewhat in the middle of nowhere. We did have our friends from Michigan Tech come down and do a bathymetry survey, which gave us a depth profile of the river all around the areas we were interested in. And this is way out of the realm of where we'd be, but it was very nice information to have. So, and it's also so Dr. Brubaker can do some modeling and actually model the flow around our site.
That's depth.
Yeah.
Applied.
Yeah. So blue is very shallow, red is very deep. So we're actually.
What's the average depth?
The average is about it's this yellow, which is 3 to 3.5 feet, and which is about right. Now obviously since it's a tidal site, it changes with the tide. But we go out there and they would be anywhere from here to. But So why do we select a tidal site? The idea of the tidal site is the tide coming in and out would move the sediment around a lot and kind of give us a scour, kind of a virtual scour event that we could use to test our system out. The drawback we found out is that tidal sites don't typically have very high flow. So now when we went out there and measured it, the flow was anywhere from, it could be as low as 0.01 meters per second to 0. So we actually needed to invent a whole new type of sensor to actually monitor this flow. Something much more compliant than our whiskers. And for that, we looked to seaweed. So our next sensors are bio-inspired from seaweed. And the idea was to just get something that was almost floating in the water, so extremely compliant. And as the tide came in and out, or just as the slightest oscillations occurred, the seaweed would just float in and out, float about like you see in the video. And so to imitate the seaweed, we actually used a piece of fabric which we attached a magnet to, about 5 millimeters below our Hall sensor. So now every time the seaweed moves, the Hall sensor picks up a different magnetic, the magnetic induction gets either stronger or weaker to the Hall sensor. And so what one of these looks like constructed is right here. Like I said, we had the fabric to mimic the seaweed. We had here's our magnet, and then Hall sensor is embedded right here in the plastic, monitoring what I'll call the y-axis here, or the up and down axis. So the placement of the post, we did put one post on the north side and one post on the south side of the bridge. And each of these are hardwired to a base station. And the base station contains our DAX and battery. And so I mean, that's essentially it. So we're just putting one on the north side and the south side. Unfortunately, and this will be more relevant when we get to the analysis later, the south side we had a little problem that we couldn't get. Let me get to the installation before I start talking about that, because it's not going to make sense otherwise. So our first post was extremely bulky. It's our first time, so we're very nervous about our post getting up and leaving us. And so it was 14 feet long, encased in 9 feet of concrete, and extremely heavy to pick up. We usually make Ganesh just pick it up though, by himself. But no, so actually we had to use engine hoist to get out of here, and an excavator at the site to actually lift it, and it required extremely heavy-duty equipment. This is our foreign exchange student that was with us for a while, Koshi, apparently cleaning off the drill. And so to install it, we essentially dropped this called a hollow stem auger, this large drill bit that's hollow inside, and plugged at the bottom so that so that sediment doesn't rise up into the middle of it. And we drill it down, and then drop the post in, stick in a pole, knock out the bottom of the plug, pull the auger out, leave the post. So nice simple process, as long as you have massive equipment to do it and experts like we did.
Did you sink the whole concrete section, the 9 feet? Or
Yeah, we sunk the whole thing actually. We buried it 13 feet down, so we wanted to leave only a foot. And this is what I was alluding to earlier. Yeah, it was pretty cool. This is what I was wanting to allude to earlier. On the first post, we had trouble knocking out the post, or the plug at the bottom. So we had to raise it a little, and then hit it out, and then try to put it back down, or fill it with some rock and put it back down to the right level. Unfortunately, the gravel that we put under it, kind of slithered away on the south post and just sank our post. Not deep, it's still right at the surface, so if we have a good scour event, we'll see it, but it sank it down enough that we don't have any sensors on this south post sticking out. So it's just more pictures of the install. This is Tom Hughes. Him and his guys helped us with the installation, ran the installation, and all the heavy equipment. And Dr. Na, myself, Koji. Don't worry, Ganesh, you're in here somewhere. Yeah, you'll be in. Don't worry. And here's the DAC box that we have bolted outside the bridge. Here's the 12-volt batteries that we're using. Ironically, they weren't a problem. Not ironically, but they weren't a problem with the original DAC because we only had 4 sensors, so it wasn't having to regulate all that much power. Where in the future, we're trying to use it with more, and that's when it started overheating.
It doesn't look very waterproofed.
It is not. So in this one, the box itself is waterproof. So it's like an electrical box. It's not the river. It's high enough so the river won't reach it.
Just from rain, or I guess you don't leave it there too long.
Oh, oh, sorry. So there's a cover. There's a cover that goes on it. It's so this is like your standard electrical box you have outside.
Okay.
Yeah, sorry. I should have mentioned that. That's what it was. And so yeah, cover it, and the box itself is waterproof to keep the stuff out. So this is a. We're going to look at the data next. So this is just the sensor configuration. The top two sensors are actually at the very top of the post and level, and then each sensor is 6 inches back after that.
And the top of the post is underwater or out of the water?
So on the south side it's underwater, so all the data from that looks the same. It's one straight line, so I'm actually not... Sorry, yes, sorry, under mud. All the post is underwater, yeah. Sorry about that, yeah.
Okay.
Actually, I'm going to come back to that one. Got out of order. Sorry, here we go, okay. So this is what does, once again you see the sensor placement here. So when we took this data trace was taken, this is what the post looked like. Buried up this to the bottom two sensors were covered and the top two sensors were in the flow of the water. Unfortunately, when we looked at it, sensor 3 was disconnected. So this is actually just a drift. It's actually just a DC drift. But sensor 1, sitting out in the water, is nice and light and kicking. As you see, it's fluctuating with even the small fluctuations experienced at the tidal site. And then sensors 2 and 4 are nice flat lines that indicate a buried sensor. And if we look at this over time, it's even more constant. You can see in between the low tide and the high tide, where the flow would be the greatest in transition, you can see the actual velocity and magnitude of the fluctuations pick up. And while these remain buried, or pick up on the top sensor, while these two buried sensors remain static. And so, so what's the power requirement of the DAC at this site? This is something we also want to calculate, so we know when to go and change the cards out. The DAC power requirements, the Arduino board itself with the pre-made platform, this is the initial prototype we used, took 150 milliamps of power at 5 volts. The AT Tiny, the little microcontroller I had to turn on and off the DAC, was 7 milliamps. The sensors each take 9 milliamps, and there are 4 of them on each post, so 36 milliamps. Our battery could do 35 amp hours. It's a nice car-sized battery. And so you get a total consumption of 193 when it's awake, when it's actually taking data, and when it's sleeping, only the AT Tiny is remaining. So if we sample once every hour for a minute, you can get about 144 days out of that. We did experience a problem when where this AT Tiny kept restarting itself, but this time not due to the heat. This was back when before I had built the handmade DAC, and I didn't realize the importance of things such as decoupling capacitors for the power, or the need for a pull-up resistor on the reset pin, or it just floats. And so we were able to mitigate that problem as I just learned more about electronics. Hot step here, so we learned a whole lot of lessons from this first installation. These are just 3 of kind of the primary ones. The rest are expansive and just we implemented along the way. We realized that the post size could be drastically reduced. We don't need a 9-foot section of concrete on it, and it doesn't need to be 3.5 inches of steel. We still want it to be steel, but not 3.5 inches of it. We also realized we could make it a square. The reason that first sensor became disconnected was that we were having trouble getting it to stick onto that curved surface as strong as we wanted to. So going to a square, it made screwing things in a little bit easier, made everything a little more sturdy. And we also realized that a river with higher flow velocity is probably a little bit better for our proof of concept. And actually another lesson that's not on here that is very applicable is to get some truly waterproof wire. The wire we were using, suppliers seemed to be very reluctant to guarantee a wire to be waterproof, and the only ones that we could get as water resistant were 18 gauge extremely thick wires. So we had to step down, we had to stick little wires into that, and then and it just basically turned into a mess. So that was a high priority for the second installation too, was to get some truly waterproof wire, which we actually had to get custom made ourselves. So the second install site is near Frederick, Maryland. And this install site actually has a problem of lateral riverbed migration. And this is where the river is essentially shifting. So it's going from flowing nicely under the bridge and moving right. So now it's got this hard turn. This is the bridge, this dark spot. It's got a hard turn left or a hard turn right. And it's essentially eroding away at the riverbank. And that's a problem because there's a road at the riverbank. Before all these rocks or riprap were placed down, the road was almost completely exposed. So lateral riverbed migration is a big problem for the Department of Transportation. And we have to alter the way we actually install the posts as well. So now instead of vertically, we want to know how far the riverbank's eroding instead of the bottom of the river. So we simply turn them on their sides. And now as each new sensor is exposed, once again we have it oscillating in the water. Once again, let's look at the power requirements for this new post. Now that this is when I started using a handmade jack, so now we have a 70 milliamp active use power consumption when it's active, and so just saving power. And we actually have a true sleep cycle, which is essentially 0, but we'll say 0.6 milliamps. The sensor power requirements has gone up to 117 milliamps. So now the sensors actually way outweigh the DAC cord, which leads me to believe for future we actually might want to look at finding some lower power hall sensors, which is something Dr. Flato is actually hearing for the first time. So battery capacity, same battery capacity. We took it down to 6 volts, but used 2 batteries in parallel. Which is something I once again wouldn't have known to do before this project. So that our total power consumption comes out to about the same, but we've over tripled the amount of sensors we can do, from 4 to 13. Sleep cycle is virtually 0, so 1/10,000th of a milliamp. And so, as I said before, you have to do 4 minutes of sampling with the handmade DAC. There's 4 different ADCs that you have to query. And so 4 minutes of sampling, 56 minutes of sleep. So with the handmade DAC, you can get about 115 days. And with the PCB DAC, I designed it so you could actually turn off the sensors you weren't currently monitoring, and this increases the life expectancy to 202 days. So not terribly longer than the initial DAC, but sensing a lot more whiskers. So we went out to survey the site, and we decided to put one post in the air and 1 post in the water. Because since with the seaweed sensors we're so sensitive to the water, we figured maybe they'll work in air as well, which would be great for this lateral riverbed migration, so we can see what it's doing at every level. The posts we built and constructed were much smaller. The seaweed sensors are now made so they hang vertically down in nice, simple circular shapes, since these are going in horizontally. They're about the same length, but no concrete and a much smaller cross section. These guys could actually be handled by hand, so it was a big improvement on the over the previous post. And so we decided to install on a very warm, sunny day. Not the coldest day of the year.
January, was it?
Yeah, it's January. I remember looking at my car, it was like 2 degrees. It just so the rest of the days around it were fairly warm. It just so happened to be that day froze. I gotta say though, Dr. Flato spent the most time in the water. She acted like it was nothing.
Are you doing?
Yeah, exactly. And Ganesh, see, you're in here. And so to install these, we actually hired a crew to do some horizontal drilling, kind of like you do to lay wire or piping. And they started about 30 feet away from the install site, just drilled in, kept track of the depth and horizontal placement using this doohickey. I'm not really sure what that is. I just know that that's what they were using. And
You have to start that far back just to get a roughly parallel.
yeah, that was
Is that why you?
that, and the posts themselves were, if I remember correctly, 10 feet long. And so yes, to get a 10-foot pole that long parallel. Actually,
roughly
yeah,
horizontal. right?
Yeah.
Is that what you're shooting
Yeah,
for?
and although we did dig down, so it wasn't just that, but yeah, it was. So these guys would go in, and if this is a river, actually, okay, there's no riverbank on the side. So if the black area is a riverbank, they come in and they go straight. So we did need them to, we did need that a little bit of that room to do it. And then so actually, you see, we actually, as the drill came through, oh dang, I didn't picture that. So as the drill head came through this hole in the bank, which now has a post in it, we actually attached our wiring to that drill head, and so as they pulled back, we fed in the post. So we fed in all the wiring, and as the post came down, once again, we can handle it by hand this time. Dr. Flato, Dinesh, and I were there to receive it. We fed it in as the, there's actually wire going in. We fed it in as the drill pulled back, and got it secure. And we packed it as well as we could by hand once it was in there. And so this is what it looks like when they were all installed. So as I was saying, we did pack it as well as we could by hand, but we found out that the earth does a lot better job of packing sand than we do with our hands. And so we got these codes, which actually concerned us because obviously a scour monitoring system, we don't want to cause scour. But we do think that this was a result of not scour itself, but from us drilling. So we are trying to figure out how to pack that in better. And now that the code is there, it could be more of a scour threat as the water can kind of hoop over the post and circulate in this area.
It seems to me if you could drill a smaller, tighter hole to fit the post into
Yeah,
initially, maybe from the outside in, I mean from the river in.
Right. Yeah.
I don't know how you do it.
No, that's actually, and that's kind of something we'll be looking in the future. We'll probably use this thing called. We're trying to simplify not having to use big machinery. So for these, use something called the mole, where essentially you dig a hole on one side, put it in there, and it would just mold through until it came out the other side. The problem you weigh between being nervous that you're not going to be able to get the thing in there,
Right.
and leaving a little space. And to be honest, actually, I think the drill hole wasn't actually this big. I think it just weakened the soil around it. The drill hole was only about this big, and the posts were this big. So it was close, but it also weakened the soil around it and kind of caused it to fall down. So and these pictures are a little deceiving. They're not. They end like right there. It's not like it's way back in there, which is good. So I think this is just mostly at the mouth, and you actually get a close-up of it in our nice video here. So here's what it actually looks like underwater. You see our seaweeds are flapping away, giving us a nice signal. And so yeah, you see that cove doesn't actually go back all that far. So yeah, we actually had 2 magnets on the seaweed and 2 sensors for redundancy. So now if we lose one sensor, we'll still have one. Glad we did that because actually that sensor had one that died, so now we still have a sensor that works. We also wanted to experiment in the future with adding up the 2 signals, see if we get a better noise to signal to noise ratio. Yeah. This footage complimentary of Dr. Flato. I tried to get a scuba ball out of this. I said, listen, I tried to get this installed in a deep fridge, like, then you can get scuba diving qualification, right? So this is what the sensor actually looked like. This was taken a little bit after that video, so two whiskers were fully exposed, the third one was kind of exposed. Exposed enough for the fabric to flop around. So you get very, very distinct dynamic signals from the whiskers on the ones that are exposed, and perfect flat lines on the sensors 4 and 5, which are buried. So this side was very exciting. It seemed just very clear results, very resounding success. So if we look at the air post, it's once again the same kind of deal where 2 of the first 2 sensors were completely unearthed. The third one kind of unearthed, and air post it made a difference. these signals will change depending on the weather. Obviously, on a windier day, we get a much better signal from the air ones. They do work, as you can see here. These were also kind of protected by that cove, so it takes a windier day for it to really get in there. So still working with getting the air signals stronger, but on a not so windy day, we're still getting a half decent signal, and definitely a discernible signal. So you've seen a lot of the seaweed data. Our whole point was to do this with whiskers. So we finally got to it, if you will. So we finally got it figured out enough that or smoothed out enough problems that we could install this whisker cap on the second post. When we buried this post, we actually left 3 extra wires to add this cap. So the cap is something I designed in CAD. It just has 3 placeholders for sensor holders, and you can actually interchange what kind of whiskers you want. So we wanted to see if maybe adding a tree whisker to the air one would help the signal. So it made it so it was interchangeable between the DACs, or interchangeable between the caps. So here's a close-up of the cap. You can see them, they just easily screw in, and here they are installed out on the actual site. And these, thanks to Dr. Na's extremely thin whiskers, came out very nicely as well and successful. So these are, this is actually not how we normally had it, but this video was showed so these are horizontally placed, so you have 3 whiskers sticking out and the flow coming this way. The data we're about to show actually had them like this, which is what we'd like to do anyway. But the video for that was it wasn't very clear, and it looked the same to similar. But you can see the whiskers are bouncing around here quite a bit. And giving us this signal. So the whiskers in the air were, visually you can see they weren't moving at all. So we used them as our control. And so these are the whiskers in the air. These are the whiskers that were in the water. And you can kind of see in the signal that there's something going on there, but it's not quite as clear as you'd like to. So we took the Fourier transform of this, and basically took something, and you can essentially see between the in-air whisker and the in-water whisker, in the lower frequencies, which was what we were seeing in the video, the in-air response is doing nothing. The in-water response has a higher magnitude as several of those lower frequencies. So this was very exciting because it was the first showing that we could actually, it was our first display of the actual whiskers working in the environment. So this was a very happy day when we figured this one out. So in conclusion, this is what we did, what my main role is in the project. Created 2 wire-inspired flow sensors. They were created and tested, one using magnetostrictive materials, one using seaweed. We designed and tested several different holders for the different kind of posts that we had to install them into, and improving those designs over time. Designed the wiring configurations for getting the data from the sensors to the posts, and as in how many wires, what kind of wires, waterproof or not, or how waterproof. Designed 4 different DAC systems, each improving on the other through the generations, and the 4th one's going to be fielded here shortly. Designed several tabletop prototypes like this one, and another one that had 16 sensors to test the viability of constructing the magnetostrictive sensors, and just to test how well they work. I did a lot of managing. I managed a lot of undergrads and managed the overall creation of the system for both the 2 vertical scour monitoring posts and the horizontal posts, and took a lot of those lessons learned and applied them to the second install site. And a lot of that was shown in just how much easier the second install went. It was done in about half the time and a lot more ease. I also designed and fielded a whisker cap and attached it to the second site, which was the first demonstration of the whisker sensor in the field, and also in this project was also the first was the initial design of the seaweed sensor and the first fielding of it. And data from each system was at the install site gathered, analyzed, and discussed in this presentation. And so that was my project, and I'd obviously very much like to thank Dr. Flater for being an excellent mentor. The story I always like to tell is that there were several nights, especially before the installs, we were here until 1, 2 in the morning, and she was always there too. It was nice. She wasn't just instructing her students to do it, and she was usually volunteering for the stuff none of us wanted to do. So she's a epitome of lead by example, and so it's been great to work under her. And I'd like to thank Dr. Na and Ganesh for making the whiskers, Ganesh for helping in basically every aspect of the project, and several undergrads such as Kyle that have helped out with the project, and Dr. Brubaker for advising us on all things civil engineering, which we are not familiar with, so you've been a great help. And actually, Dr. Bowden, to you for letting us use your labs to construct our posts. That was unbelievably helpful, and I'm sure all the rest of the labs were appreciative as well that we weren't constructing posts in the middle of there. And yeah, also the guys from Toros, Dr. Flater's company, were really helpful, including her brother, who we unfortunately lost along the way, but who was a great influence to the team and was just very nice to have around. Always had a smile on his face, got you excited about the project. And also Tom Hughes and his crew, those are the guys that helped us to do the actual installation. And finally, all our friends at Michigan Tech that were also collaborating with us. So, and the people that funded us, how about them? It's essentially Maryland State Department of Transportation of Michigan, Department of Transportation, OSTR, which is this very long Commercial Remote Sensing and Spatial Information Technologies Program, and Research and Innovative Technology Administration. So, that's all I have. Does anybody have any questions?
Open the floor for questions to anyone. Start with Mr. Bowden, we'll come back to you.
I think we should start with the new master.
Any questions?
Any derogatory comments about that?
Well, I actually have a question.
Sure.
Sort of tying in all this multi-dimensional thingy project that you've done with what I'm doing, the modeling study project. When you look at a particular bridge site, the two bridges that you looked at, is it obvious where you should put the sensors, where you should put the post?
For our purposes, it was, but I wouldn't suspect that it would always be that way. So we were putting them into sites that were known, that had known scour issues, to the point that it was very visible. Like the lateral migration, we saw where it was going into the road, or we got in there and you could see where it's just starting to carve out a circle. So for us, it was very obvious to put it there, but that bridge is also going to get replaced in a year. So I wouldn't suspect that all sites are like that. You know, if you have a bridge that's only 10 years old, it might take a Hurricane Sandy to make a bad scour. And in that case, you could look at maybe some flow patterns, but other than that, you can just, you see flow going this way, and all of a sudden, just one area is slowly coming back, not causing any problems yet. You can see how that would turn into a spiral. So, not completely obvious, which is why your modeling would be extremely helpful.
You're not just saying that.
No. In fact, I was trying to pretend I knew more about scour than I actually did. No, but yeah, it's extremely helpful. Yeah, like I said, the only places it's obvious is in bridges that you already know it's a problem.
But isn't the long-term vision to make these things so cheap and easy to install that you just put them everywhere? You can't.
Exactly.
Everywhere there's any concern at all.
Yeah, and so there's actually two goals for the project. One is to have it installed on new bridges, which is the installation process to be easy, just stick it right in there.
Yeah.
And then, yes, you're right, for existing bridges, which there are thousands, the idea is to be able to make a really cheap post that you can put anywhere you want. And that's why we want to try to keep the DAC simple, try and make it low power.